Good afternoon. I wonder if you have followed the news yesterday about the gravitational wave. Saw that? Yes, 100 years ago, Einstein's general relativity prediction of gravitational wave. And actually, I don't know if you noticed that we have just talked about mass and energy conversion. And if you recall, it talked about this time the measured signal it was from two black holes with the mass of 36 times of the mass of the sun, and the other one is 29. Anyway, there are a lot of details, but this is particular one. So the two huge mass black hole, and they merge to become one. And the one black hole's mass was 62. So 36, 29, that's 65. And the outcome, 62. And the 3 disappeared, becomes what? We talked about defect, mass defect, the energy mass conversion, and so the mass disappeared, become the energy that past this billions of light years and being detected. So that's what we are studying. Of course, that's more what we learn is only the very basic part, but it should give you a little help of when you understand this very phenomenal, very how would you describe it? Just extraordinary scientific discovery. So what we are learning actually it's very microscopic, not really the daily happening, but we can relate it either to this astronomy-related physics, or later on today I'll be talking about nuclear medicine. We'll see this very amazing physics in work, in reality. So last time we talked about the decay, the different type of radiation decays: alpha decay, electron decay, positron, and gamma, all different emissions. And then we started some equations, decay equations, and these two equations are the formula we can use to calculate the activity, the A, or the number of atoms, N, as a function of time for radionuclide. Lambda is a decay constant. And what's the unit of lambda? Per second, yes. That's per time unit. It could be per minute. Rarely people use per hour, but it could be per hour because the definition of the activity is how many disintegrations or decays per unit time. So it could be, it must be a time unit. it could be second, minute, hours. Okay. Okay. So with the equations, actually you will have some homework doing some exercises. Just solve the equation given the activity at time 0 or time A, and given the half-life or decay constant, you will calculate the activity at a later time or prior time. You will have that practice. One other group of questions is related with this activity mass correlation, if whether you can figure one from the other. So the basic formula is this: the activity is equal to the decay constant multiply the number of atoms available. That's actually where we started the definition of the activity. So if you are given a certain weight, mass of a certain nuclide, if you are asked to calculate the activity, can you do that? Yes, you can. Here is a process. So if you are given the mass for a particular atom, in this case, let's say element X, for this element, the atomic mass number is A. So if you're given this, the weight or the mass of the element, W sub X, then you can calculate how many atoms of this element there is. It will be calculated. First, you divide this mass by the atomic number. So this will convert that mass amount to how many mole you have. And we know that in each mole, the number of atoms or molecules, it will be that Avogadro's constant, 6.02 times 10 to the power of 23. So if you multiply that number, now you get the number of atom in this case, and you have that N. For a radionuclide, once we know which kind of a radionuclide it is, we have the either handbook or a table somewhere. Everything, some information, including the decay constant, or most of the time, the half-life is given. You can find it. So with the half-life, you can figure out the lambda, the decay constant, or vice versa. And now you have lambda and you have N, and you can calculate the activity. Here is a slide on about half-life. We mentioned it briefly previously, and in this slide, it shows you the relationship of half-life and the decay constant. So first, half-life is the time it takes for certain amount of atoms decay to half of the number of those atoms. So with the original equation, the decay equation. And if we assume an unknown t equals to t half, this is the half-life. And we, by definition, at this time, the number of atoms will become half of when it starts. Half when it starts. And if you put that condition in this equation, and this n0 is the starting number of atoms, cancels, and you have only this t half unknown. It can be derived at this number. And with this, you can also express that the decay constant is equal to 0.693 divided by t half.
To the class and to Dr. Yao, this equation is almost identical to the equation that you'll use for calculating the half-lives of drugs based on the elimination rate constant. Here, we're dealing with radioactive decay constants. It's the same principle, though. It's just achieved differently. This is through physical, through atomic decay. But you'll be working, it's great. I love this because this is the exact same stuff. It's so simple. It seems complicated, but it's really just a beautifully simple relationship that's there. So he is teaching you pharmacokinetics. You just don't know that yet.
Yeah, actually, you will see the very same formula. We change the expression a little bit, the symbol a little bit for the attenuation. It's a very same equation. We got this decay constant replaced with attenuation coefficient. And we also have the half value layer. But the mass is the same. And we just gave it a different meaning, real-world meaning. Either the drug half-life or the decay half-life or the attenuation half-value. They all based on the same math. That's what's really really amazing of this basic science. The math is the basic science, the physics as well, and including the discovery of a gravitational wave that we learned earlier. It just have so many aspects you can extract. Okay, so we have the basic decay equation and half-life, and you can practice a concept of the average life of radionuclide, knowing that at different time there are different number of atoms decay or disintegrate. So some they short-lived, some decay at a later time. And what's the kind of average lifetime overall for this amount of atoms? Here is a kind of a practice, an exercise for calculating the average life or T mean. It's assuming the starting number of atoms is n sub 0, and the mean life of the atoms of this radionuclide atoms would be basically the time for each group of atoms, the life, divided by total number. Just like we calculate the average life, average life of people, have, let's say, 3 people, 50, 60, 70, well, that's a little young, let's say 80, 90, 100. So the way that you calculate the mean is 1 times 80, 1 plus 1 times 90, 1 plus 1 times 100, divided by 3. And same idea, just exercise. Okay, so that concludes our lectures on the where radiation comes from and some basic quantification. So now I'm going to start another chapter, which is about radiation interaction with matter. Why we do that? Because radiation, although the basic science, great, it has so many potentials, but for us, our curiosity also relate with our practical purpose for using this knowledge, the knowledge we learned. So for radiation, we wanted to use it, let's say, for medical imaging purpose. That will depends on how we detect the radiation. That's just one type of application. So we are going to learn how we can detect radiation, and that's where we start. Why we start the interaction of radiation with matter. And the other aspect of understanding how radiation interact with matter is also for our protection. Radiation is a mysterious thing, not to mention the gravitational wave, just the gamma ray, more kind of simpler radiation. It's not visible to us without particular special tool. So we need to know it, to benefit from it. Otherwise, it could do the harm. That's the dosimetry, the exposure, the dose, and that aspect that we are concerned. Okay, I'll skip this part. Okay, this is the homework for the second lecture. I have 2 questions. But I have more questions, practice questions, uploaded on UB Learns. Have anyone looked over the practice questions? The sample exam? Okay, yes? Oh, okay. Looks really difficult. If you have some questions, you can bring. We can just talk about the questions in class. Okay, including the practice questions. Okay. Okay. The third lecture or third chapter is about interaction of radiation with matter. That serves the purpose of the theory behind radiation detection and the design of radiation instrumentation. The radiation that we are concerned, or this lecture or this course covers, include alpha particle, beta minus, and beta plus particles. And those are charged particles. And also we are very interested in gamma radiation. That's the primary radiation that we rely on in nuclear medicine imaging. We are going to talk about why we use gamma, not alpha, not beta. X-ray, as we talked about previously, it's also high energy photons. The reason is the name is different from gamma. It's because the origin are different. It's related with electrons, and gamma is related with nucleus. When we talk about radiation interaction with matter, we are really concerned only with the nucleus and electron, because at this level, very small scale, the radiation, the charged particles or gamma rays, what they see are really only electron or nucleus. So that's the other party of the interaction. The interactions between the radiation and the matter, there are kind of two categories. One is electrostatic. It's basically you have charged particles, and the nucleus has charge, so have this interaction. And for the X-ray or gamma ray, they are not charged. They don't even have mass. So the interaction, you can imagine, it's collisional, although the gamma or X-ray, you can consider they are wave as well. The general interaction, you can just summarize it as energy transfer, all the interactions. The specific subcategory of the energy transfer are excitation. That means the energy transfer elevate the energy state of the target to another level. Or ionization. Ionization means you have ions produced. So if there's an electron being ejected from the atom, now you have the charged ion, and you have the electron. They are both charged, so that's called ionization. Bremsstrahlung does not fall into that two category. That's when X-ray, that's specifically when X-ray interact with matter and have a dramatic change of direction, and this corresponding to a electromagnetic kind of a wave change, and that causes some energy release, and the energy release in the form of photons. That's called Bremsstrahlung or X-ray. And this knowledge, so we have the radiation types and the matter in terms of electron and nucleus, the interaction. And this knowledge, we could use this knowledge for our radiation detection design, or develop our principle for radiation dosimetry, or to protect ourselves from radiation. So let's start with charged particles interaction with matter. Here, this slide shows a couple of diagrams. We have the charged particles. Here it's an electron, and it could be replaced with a positron or alpha particle. They are all charged particles. So when a charged particle approaches an atom, most of the time, because most of the space occupied by electrons, so it will mostly interact with electrons. If the incoming electron passes a small fraction of its energy to an orbital electron, it will pass some energy to the orbital electron and elevate to another higher level. This is called excitation. And this excitation, this elevated energy level, may later come down, and this transition will create some energy release. It could be, like we mentioned previously, X-ray, or some kind of a photon energy release. If the energy transferred to the orbital electron is large enough, it will overcome the bending energy of the orbital electron. And in this case, the electron will be ejected from the orbit, and therefore you have the ionization. And the ejected electron will leave a vacancy behind on that orbit, the orbit of the electron. And this later on, if this vacancy is filled with the outer or higher level electron, then there will be X-rays released. And the third case here is if the charged particle electron happen to approach the nucleus, because nucleus is much heavier, and it has the interaction which may dramatically change the path of the electron, because the electron is much lighter. For one mass unit of atomic mass unit, it's about 2,000 times of the mass of electron. So the electron is much lighter. So the interaction will have a much significant impact on the trajectory of the electron. And in this case, so you have basically the electric wave produced, and which will generate an emission of energy. And this emission of energy is called Bremsstrahlung, or X-ray. So we have these three types. And we have here, it just describe a particular term called the delta ray. So when the electron eject another electron from the orbit, if the ejected electron has enough energy to create some additional ionization, and it's called a delta ray. So that's the general interaction types of charged particle with matter. So it's pretty systematic. The incoming party is electron or the charged particle, and the receiving side, you have nucleus, you have electron. And the interaction creates energy transfer. Depending on the amount of energy transferred, you may have excitation or ionization. And if the interaction involves this major trajectory change, like the Bremsstrahlung case, there will be this X-ray produced. Okay, so now let's look at the characteristics of like highly charged particles interaction with matter. And here is an illustration of alpha particle. Alpha particle is the nucleus of helium atom. So it has 2 protons and 2 neutrons. The 2 protons and 2 neutrons, that means the mass of alpha particle is much heavier than electron. It's about 8,000 times that of electron mass, and also has 2 positive charge. So for this heavy charged particle interacting with matter, the result is quite different from when an electron coming to interact with matter. And here is just a kind of a diagram showing the secondary electrons. Secondary electrons are electrons kind of ejected, produced from interaction. So you see a kind of a straight blob of these secondary electrons. So imagine that this nucleus of helium or alpha particle move in this direction, and in its path it creates this cloud of secondary electrons because the energy transfer, because of the interactions, the alpha particle with the matter's electrons. It's straight because it's very heavy compared to the electrons in the way. So it doesn't change. The alpha particle does not change its trajectory straight. And it has many secondary electrons produced because there are a lot of opportunities of interaction of different alpha particle and electrons because it moves slowly and has 2 positive charge. So have plenty of chance of passing energy and creating secondary electrons. This is a graph basically showing this kind of image. So vertical axis is ion pairs per millimeter, per unit distance. And the horizontal axis is the distance from end of range, end of its trajectory. And so you can see near the end, there are more ion pairs produced because at that time, the alpha particle almost lost its whole energy because previously just loose energy becomes slower. At the end, it's very slow. So there are more chance of interacting with the electron and the loose energy. And this slide, this graph on this slide shows the alpha particles range. So this is how far the alpha particle can get into the matter, the interacting matter. And this is the relative number of alpha particles at each depth. So imagine that we have, let's say, this matter, and you have a beam of alpha particle hitting here, and you look at in like a virtual environment, you can see, imagine you can see how many alpha particles get into like 1 millimeter, 2 millimeter, or until certain thickness. So this is what this graph is. You can see it's pretty flat. That means however many, the number of entering alpha particles will pretty much stay the same number, get into certain depths. And at certain level, all of them more quite uniformly, they come to an end. Okay. Questions, please. I think I lost you. Did I? Yes.
So where would the end of the absorber thickness be on the graph?
That depending on the energy of the particle, of the alpha particle, and depending on the material. Here, the illustration is emphasizing a very specific characteristic. They all reach a similar, very similar depths. Okay, but it's a very, very good question. Yeah. And the reason that it all reach let's say imagine that you have 100 alpha particles. You can say that until the very last segment, all of them reach there. And there's only a kind of a slight variation. Some disappeared a little bit before that, some a little bit further. The reason behind that is because the alpha particle, they are heavy, so once you have one direction, they all go the same direction. So the probability or the number of interactions they lose energy, or the rate they lose energy, are kind of uniform. So one particle alpha compared to its neighbor, they are going through the same process. And we'll see that see the difference when you look at like an electron. And electron, they may change dramatically the path. So one is very different from the other. So it will not be flat. And every electron will have its own trajectory, very different from each other. And these characteristics that you can predict where all the alpha particles can reach, and it's straight, and it lost most energy or create most ionization at the end. It's a very has a very important application in radiation therapy. Radiation therapy is about delivering radiation energy to a target. So given that you know the alpha particle can go straight, and you know where it releases energy the most. Now you have the ideal radiation therapy tool. So that's what we can relate the science with the purpose. Okay. So the top drawing is about alpha particle, and these two are illustrations of beta particles. And now you can see this is like the path of the incoming beta particle. You can see the pathways are kind of a more zigzagging, kind of changes direction dramatically. And this is because electrons is much lighter. When it interacts with the other electron, they have an equal mass. So an interaction, there's no advantage in terms of, or preference in terms of the direction the incoming electron prevail in its own pathway, because it doesn't have the mass advantage like the alpha particle. So it's just like two balls with equal mass. They will, when the interaction happens, the direction just depending on the angle of interaction. It doesn't have that characteristic of alpha particle prevail going one direction. So that's kind of one important difference from alpha particle interacting with orbital electron. And the other characteristic is electrons, they are lighter and they are faster. And each interaction with the electrons, orbital electrons, does not lose that much energy. So it goes farther. And this is a graph showing the depth of electrons can go into a material, and this is relative number of the electrons detected at different depths. Now you can see it's no longer as flat as the alpha particle graph we saw. So you can see it just quickly, this is a log scale, it quickly reduces. That means from the very beginning, there are a lot of electrons lost from its original direction, because they are easy to be bounced away. And there's no like ending thickness or range. If you remember that for alpha, it's pretty clear. Rather, here it's reduced significantly, but there are particles somehow can go even further. And that could be because some electrons, they may create this Bremsstrahlung. When they interact with, by chance, with the nucleus, and it produces X-ray, Bremsstrahlung X-ray. This X-ray, and in turn, it will create new electrons. So it just extended the range of the electron beam. both alpha particles and the electrons are charged particles. Charged particles means when they interact with matter, they have the electrostatic field surrounding the particle and interacting with the electric field of nucleus and the electrons. So that makes the probability of interaction kind of high. And probability of interaction means high probability means high number of interactions or losing energy. So they lose energy kind of fast. And that means it cannot go that deep or that far. That means low penetration power. The mean alpha particle emitted by this 5.49 MeV amerium is 54 micron in soft tissue or water, and that goes only 4.2 centimeter in air. Electron, for the same type of material, the range would be 0.4 centimeter in water and 309 centimeter in air. That means can go much farther than the alpha particle. So that's implication of these properties of this alpha particle and beta particles are, if you are considering designing a detection instrument, then for both particles, because they don't penetrate penetrate well through the matter, so your detection instrument, if you have let's say have a pretty thick cover, then the particle may not be able to reach your sensitive detector. So that's big concern, because it's so easy to lose the alpha particle, especially alpha particle. So you have to keep the window open to receive the signal. If it's for radiation dose concern, these charged particles are pretty dangerous. They can make large amount of energy deposition because it cannot go far. It just before it penetrates, it just lose all the energy there, like alpha particle. So you know that the main damage from smoking is through the alpha from alpha particles in the tobacco leaves, and this is why the alpha particles they will deposit all its energy in a very short range. So if it's attached somewhere inside or breathed in, then it will do the most effective damage. Okay, so those are the charged particles interaction with matter. The interaction of photons with matter is different from because photons are not charged. They don't have mass. So that makes them kind of more penetrating, or interaction probability with the electron or nucleus become much smaller. So they are more penetrating. The interaction mechanism of photon with matter, there are three types of interactions: photoelectric interaction, Compton scattering, and pair production. before we get into each specific type of interactions, the overall effect of interaction is the absorption. You can consider it absorption of the photon. It's kind of described by this formula. So if we have a beam, or a beam of photon, I consider it a flux, okay, a flux or fluence, like a uniform fluence for a certain area. The absorption rate or fraction that being absorbed by this uniform material is proportional to the thickness of the material. And the fraction or the constant of this fraction and the thickness is represented by this called attenuation coefficient. This attenuation coefficient, intuitively, it depends on the energy of the photon and depends on what kind of a material that in front of that beam. So you can see this is a parallel to the decay equation that the very original definition of decay equation. So you have significant amount of atoms in front of this photon beam. Yes?
Is photon fluence made with the amount of photons?
You can, yes, it quantifies the number or the quantity of the photons. So you can imagine that, let's consider just at one, we ignore the time point, we just consider that one time moment. So you have we look at one unit area, 1 square centimeter. Imagine that we have 100 photons hit this surface. So this I would be this 100. And then suppose the thickness of the material is delta X. Imagine it's very thin, okay? And so this material will create interactions with the photon, either absorb it or scatter it. Therefore, the photons coming out from this material, the other side, will be less. So that the change or the difference is that delta I. Maybe 90 comes out, so delta I will be -10. And this change is proportional to how thick the material you put there, right? So that's and that's the kind of a proportional to this delta X. And the proportional ratio, it depends on what kind of photon, the energy basically, energy you have, and what kind of material you have. It could be wood, could be lead, could be something else. So depending on this photon energy and the material, you have a particular ratio. And this ratio is called linear attenuation coefficient. Okay. So this is the explanation, the physical meaning we it's kind of different from like a decay, but the mathematical formula is actually identical. So from here, actually, we have on another slide, we can derive the I as a function of x and mu L. Okay. So mu L is the ratio, and it depends on the energy of the photon and the material. And specifically, it depends on different interaction mechanisms of photon interacting with matter, the photoelectric, Compton scattering, pair production. And each mechanism will have will remove the photon in a certain way. The photoelectric effect is when the photon, incoming photon, hit orbital electron and pass all its energy to that electron. It's called a photoelectric effect. And the ejected electron will have the energy of photon energy subtract the bending energy of that electron. And typically, the bending energy is much less than that photon energy. So the energy of this ejected electron is fairly close to the photon energy. And this photoelectron, we just mentioned that electrons, they don't travel far. And especially if we have some material dense, like a detector material, it will pretty much consume the energy locally. And therefore, if you have a detector, and the detector had a photoelectric effect interaction with the photon, your detector will collect all this photoelectron's energy. And this energy can be converted to a signal and let you know what type of energy, what energy the photon is. So your detector will have a good information of the energy of the photon. So that's in terms of detection, that's a good event. You get good information. And also, when we talk about imaging, our detector or our sensor is to detect where the radiation hit the detector. So in this case, photoelectric effect case, wherever this effect happens is where the photon hit. So again, you get the good location information. So these two information, both are very useful for detecting radiation. So this is a kind of a desired type of interaction for measurement of radiation. Compton scattering. If a photon interacts with an electron, but does not give all its energy to the electron, rather it gives part of its energy, and then it bounces away with some residue energy. This is called Compton scattering. So it passed some energy and then bounced away. So in this case, the bounce away photon will carry partial energy. If you detect this photon, it has partial energy, and it also does not reflect where the original trajectory, what the original trajectory is of the photon. Now, your detected photon really doesn't have much useful information to tell you the original photon. And in this case, like for our imaging application, it's a bad event. It's not useful. And even for if we have the detector just absorbing what the energy that the photon left behind, because it's a partial energy, it makes it less specific, or you cannot fully trust whether this is a good event or not, because it does not have the signature of your original E sub-zero energy, the photon energy. So Compton scattering is interaction that's not useful for detection. I'll skip this slide. It just shows depending on the angle of reflection, the energy of the scattered photon is different. The third effect of interaction type is called pair production. This is another energy mass conversion miracle. So in this case, the incident photon, it must have higher energy, higher than the 1.022 MeV. Must have that higher energy. And when it comes to interact with the nucleus of atom, and it has this interaction type that it loses part of its energy. And this energy is converted to a positron and an electron. So we have talked about positron-electron annihilation that convert mass to energy. And this is reverse. So the energy is replaced with two particles with mass. So pair production. The energy is converted to mass. So the total energy, photon energy is this, and this 1.022 MeV energy is used or consumed to become one positron, one electron, and the energy left is given to these two charged particles. Okay, and so this equation describes this part of the diagram, and this diagram shows once the positron is produced, it will just start a positron journey. Positron is a positively charged particle, and it will interact with electrons. And each interaction will consume some energy. And at the end of its energy level, it will meet And electron, there will be a positron-electron annihilation. So it goes the other way. Yeah, positron-electron annihilation. And this convert mass to energy. And this time, the energy emitted will be in two opposite photons, 511 keV photons. And this, you can, the positron emission tomography, PET, remember first class we talked about PET. And if we just start from here, this is the same positron emission that we rely on in PET. Okay, let's take a break. 5:17. 5 minutes break, and please think some flip back to see what questions you have, so that we can kind of realized I did forget. Yeah, I just turned it on. Okay. 2 seconds. Saw you. Okay. Wow. Okay. So this is a summary slide of the interaction and consequently the penetration power. Okay. I'm going to kind of accelerate a little bit for the detector part. So, okay. So, the interaction theory would give us the understanding how we can design instrument to measure radiation. So now we are going to go through 3 types of radiation detectors. A, gas field detectors. Gas field detectors are kind of the simplest and cheaper, but it's still in use. If you go to any lab that uses radiation, you will see some kind of a Geiger-Miller counter, so you can scan if there's radiation spill. It's not that accurate, but it serves the purpose, telling you whether there's a spill, some contamination, just convenient. There are a couple of different types of gas field detectors, but they are also very similar. Semiconductor detectors. Gas field detector, because it's gas field. Gas is not that dense. To measure like a gamma, X-ray, they are not efficient. They pass through. You have a very small, big signal. So you try to improve the density. This semiconductor detector is solid state. It's semiconductor, so it's no longer gas. So it has higher efficiency. Also, it has a pretty good so-called antigen resolution. It can differentiate different antigen of radiation very clearly. The third type is called the scintillation detector. Scintillation detector, these are designed mostly for gamma ray detection. And most of our gamma ray detectors or nuclear medicine imaging detectors are based on scintillation detectors because it has a density and can give you the efficiency, and also now with a lot of technology development, it can give you a large amount room temperature sensors for us to do imaging. That's especially relevant for nuclear medicine or radiopharmacy. So I'm going to go over this. Gas detector. Here is an illustration. So you have a gas chamber. So you have a kind of a chamber filled with gas. On the 2 ends of the chamber, you apply voltage. Anode, cathode, that's positive polarity, negative polarity. You have the electric field formed in the chamber. Okay. Now, if there's radiation passing through the chamber, we just talked about that. Radiation interaction with matter is all about antigen transfer. So antigen transfer, one type of transfer is creating ionization, creating charged pairs. Electrons kind of extracted, ejected, leaving left the ion behind. So you have pairs of charges produced. Charged particles in air and in the electric field. They will move in the electric field, and the electric field will push or pull these charged particles. And this movement of charged particles, that forms electric signal. And with the electric signal, you can use the very original needle to say if there's a current, or you can digitize it. For the simple instrument, you can just observe the needle if there's a signal electric current. So that's the basic principle. Ionization creates charges. Electric field collects charges, and collected charges create electric current, drive your needle or some indicator. So there are three types of gas field detectors. They are using the same geometry structure. The difference is how much voltage you apply. If you don't apply voltage, there's no electric field. There's no driver for the charges to move to produce current, so you have no signal. If you apply a little bit electric field, the charges will kind of start kind of migrating. But some of they will migrate slow, therefore there's a chance they will recombine. So you don't collect enough signal. When you increase the voltage of the to the chamber, higher electric field are produced, and therefore there's faster movement, less recombination of those charges. And this region is called ionization chamber. So you just collect the charges produced and get through the recombination region. So this is the first region. If you increase more the voltage, make the electric field stronger, now the charged, let's say electrons, it will gain momentum and it will hit maybe another electron in the gas and produce another ionization. So you get another charge. So this will create a magnification of your electric current. So this is we call it proportional counter region. And in this region, there's magnification of the signal, a charge signal, and this magnification is still linear to the original charge created. And so you can do some counting. The signal will be large enough to do some counting, but you can still get the energy. You can also get the energy of the original signal. If you increase the voltage further, and now the charges, they will be accelerated even more. So for each electron, it will be accelerated to produce, guaranteed to produce another ionization. And the produced ionization will be accelerated also. So you have so-called avalanche effect because the acceleration is so significant. So once you have one ionization charge produced, it will trigger a series of ionization and produce a huge signal. So now, as long as you have one radiation start ionization, you get a signal. Okay, so that's called the Geiger-Miller counter. It's avalanche effect. And now, it doesn't matter the energy, the signal loses the original magnitude energy information. It just, as long as you can trigger it, you have a big signal. So this is a Geiger-Miller. So three types of gas field detector. Ionization chamber, you may see it in a lab. And those calibrator is ionization chamber. This picture is exactly what we have in the lab. So you have two parts. One is this kind of basically looks like it's a cylinder. Inside is a vial, and you drop your radioactivity sample in the vial, and here is the electronics part, and this is the display. These are buttons. So you pick a button. Let's say you have a technetium-99m. Press down. You preset. That means you know the radioactive sample you have is technetium-99m. Basically, you give it the knowledge that it's 140 keV gamma ray. So the amount of charge produced per each gamma photon, 140 keV, is pretty pre-calibrated. So the total amount of charge you observe in the signal, you can separate how many ionization are produced. So you can know the activity. So that's how it works. If you don't have those buttons, you have all you measure is the total charge produced, total ionization charge produced. It's a product of how many ionization happened and multiply how many particles are there, and each particle's ionization power. So it's when you have multiplied product without knowing any one of them, you don't know which is kind of you cannot separate them. But if you have a button to say, okay, each photon producing this much ionization, when you have the total, you can figure out how many photons are there. So that's if you read through the notes, you will notice this part. It's think here. You cannot count engineers. Okay. Yeah, this slide just shows the avalanche effect. So you have initially you have one ionization, and then when the charge is moving toward the anode, and it will get acceleration and create the avalanche effect. Basically, this is what this triangular shape kind of indicate. There's more ionization produced. Okay, semiconductor detector. Semiconductor detector uses the same working principle like the gas filled chamber. Remember, gas filled chamber, we have gas and we have electric field created by the voltage on both sides. And for semiconductor detector, we just replace that chamber with semiconductor. Semiconductor means there are available charge carriers, those electrons. They can move the limited mobility. So when you have the electric field build up over this solid semiconductor material, when there's ionization charges produced by radiation, the charges, the electrons from ionization, they will move because it's a semiconductor. So it kind of has some property of conductor. So the electrons will be able to move from one spot to another. The ion or the atom would not be able to move because it's semi, so it doesn't move. But when electron move in one direction, we call it hole. The hole leaves behind, it's as if it's moving in the other direction. So you still have the movement, and you have the same effect of the charges moving in the gas field. So you also create the current. So it's all about antigen deposition, create charge, and charge, you somehow collect the charge to make your signal. The advantages of semiconductor is, first, it's much heavier. The air's density is cubic meter. It's 1.29 kilogram. That's very light. The density of semiconductor can be 2,000 to 5,000 times that the density of air or the gas field detector. The density means there are more atoms, nucleus, electrons in the way of photon to do the interaction to produce the charge, ionization charge for collecting signal. So that's one advantage. So you have more probability to collect the interaction and signal. And also the atomic number Z is a couple times higher. Atomic number means they are higher, means there are more electrons. There's another advantage is the energy per ion pair in semiconductor is lower. What does that mean? That means if the interaction, photon with matter interaction, consume one certain amount of energy, in semiconductor, there are more ion pairs produced. That means more charges produced. So in other words, higher signal, more signals are produced. And more signals, that means the signal is bigger. In statistical property, when you have more higher number of samples, the statistical variation is smaller. Just like we do any survey, you want to have like a 10,000 sample, so you have a less bias. Now we have the presidential election, and they want to a lot of polls. If they just sample 5 people, easily can be biased. If it is sample 5,000, it's more convincing. Okay, so when you have more ion pairs produced, the relative variation becomes much smaller. But it has problems. It used to be only operated in the very, very low temperature, since buffalo is cold, looks that number. And also have some purity issues. So a lot of research has been going on to make room temperature semiconductor, and we have some detectors working that way, but still it's not very available. This slide shows some numbers of the properties we were talking about: the density, the atomic number. This is average energy expanded per electron hole pair. The energy for each ion pair, or how much energy you need. So let's just compare two columns. These are semiconductors, and this is, we assume it's like a gas field detector. You can see gas field detector is much lighter than semiconductor, and the Z number, this is semiconductor, is much higher, and this number, the energy needed for each ion pair, is much smaller. This is a good thing. So all categories, semiconductor is much better. Okay, so those two types of detectors. The third type of detector is called the scintillator detector. The composition of this type of detector it consists of two components. One is scintillator. Drawn here is this cylindrical shape cylinder, and attached to another component is called, in this case, is the photomultiplier tube. So the scintillator's responsibility or role is to interact with the radiation or photon. When photon deposit energy in the scintillator, it will create elevation from one lower energy state to another higher energy state in the scintillator, the electrons. And when they transit to lower energy state, there will be visible light emitted. So the energy deposited will be converted into visible light. So that's scintillator's role. And the scintillator usually only those very dense, very high atomic number, that means have a high efficiency of collecting radiation, photon, are used, and produces maximum light. So the visible light is produced when you detect gamma ray. The visible light is propagated to the interface of this scintillator with the photomultiplier tube. And the surface of that photomultiplier tube is called the photocathode. So the light, the visible light from the scintillator, it will create so-called photoelectron, because just like photon, it will hit that surface. The surface has a special material, so when it's hit by the photon, the visible light photon, it produces electron. Okay, so produce electron here. And this is a tube. This tube has multiple stages of so-called anode or diode. So you have electric field multi-stages of electric field in this tube. It's a vacuum. Once this electron produced get into this field, it will be accelerated in each of this electric field. Electron is charged particle. It will be accelerated in the electric field. And in each stage of acceleration in the electric field, the end point is a target. So the accelerated electrons will hit that target. And that target is designed so when there's a heat from electron, you produce more electrons. And the more electrons are accelerated in the next stage of electric field, and more electrons produced. And the more electrons accelerated, more produced, more accelerated, and so on and so forth. And notice this kind of wider and wider yellow stream. And the yellow stream indicates the electrons. The wider beam indicates more electrons. And electrons, moving electrons is what? It's current. It's electric current. Electric current is a signal. And this signal, at the end, it comes out and can be detected, can be collected, digitized. And so that's a scintillator detector. So scintillator detector has two components. And the first component, scintillator, is converting the energy of incoming photon to visible light. The second component converts the visible light to large electric signal. And there are different types of scintillators because that's a crucial part for your detector. And if you talk about an imaging system, like a $1.5 million system, the scintillator can be like a half of the price. The cost, the material for the scintillator, maybe half the price. It's like the most, the best material, scintillator material, the price, a year ago it was like 1/5 of the gold. So now, not sure the gold price goes up. Not sure if the scintillator price also goes up. But it's very expensive because it's a very critical component, and also because it's like a rare earth material. So you have very hard to refine and extract. Okay, so once you have this scintillator and photomultiplier tube, you have the electric signal. The rest is very generic. You can use some electronics, digitize it, or amplify it, and send to your computer. You have an instrument. Yeah, okay. Are you tired? No? Okay. Anyway, I'll stop here.